Hey everyone, welcome back to Linear Algebra. This will be lecture 4 of the course, and in this lecture we're going to get into a key operation with matrices, and that is matrix multiplication. Okay, so let's go ahead and jump into it. We'll call this section 1.4 matrix multiplication. All right, so last time we talked about what is a matrix, and we got into some of the fundamental operations of matrices. So we talked about how to add two matrices together, how to multiply a matrix by a scalar, and this time what we want to do is extend our matrix operations to full-blown matrix multiplication. How do I take two matrices and multiply them together? Okay, and so matrix multiplication is actually a generalization of the dot product of vectors. Matrix multiplication is a generalization of the dot product of vectors. Okay, and so the way we multiply two matrices together is going to have a lot in common with the dot product. Matrix multiplication is going to depend on the size of the two matrices having a certain symmetry as well. Is going to depend on the size of the matrices. Okay, and so let's talk about that. So two matrices, A and B. So I've got a matrix A and a matrix B. They can be multiplied. And when I say two matrices A and B can be multiplied, order matters here. And so I'm going to say in that order. So A, B. Okay. They can be multiplied if the number of columns of A is equal to the number of rows of B, right? So let's say A is m by n and B is n by p. Okay, so these two matrices can be multiplied together because the number of columns of A, specifically n here, is equal to the number of rows in B. Okay, so that's a key consideration when trying to determine whether you can multiply two matrices. So it has to be the case that the number of the number of columns of A is equal to the number of rows of B. And so for the kind of the way, a good way to remember this is to say, okay, if I want to multiply A times B, then I need to look at the dimensions first. So I've got m by n, and I'm trying to multiply that with an n by p. The only way it's going to work is if these two numbers are the same, right? Those two inside numbers, right? And so in this case, if A is m by n and B is m by p, you got no problem multiplying A and B. However, given the same two matrices, if I try to multiply B times A in this order, then that's like saying an m by p times an m by n, right? And so in this case, this doesn't work. This one does work. Okay, right? And it has everything to do with the dimensions here. Right here, the dimensions align. The number of columns of A matches the rows of B. Here, they do not align. Right here, the columns of B do not equal the rows of A. Okay. And what ends up happening here is when I multiply two matrices together, I get a new matrix, obviously. And what are the dimensions of the new matrix? The dimensions of the new matrix, AB, is equal to, okay, the size of this is going to be equal to the number of rows of A by the columns of B. Okay, so the new matrix, AB, is going to have this dimension. Okay, so let's talk this out. We can kind of summarize all of this nicely. Right, so if A is m by n and B is n by p, the inside numbers, they tell you something. They tell you is matrix multiplication defined? Yes or no? Right? If they match, then matrix multiplication is defined. If not, you can't do it. Okay? That's what the inside numbers tell you. The outside numbers, the m and the p, tell you the dimensions of the new matrix after you've done the multiplication. Okay? So the inside numbers have to align. They have to be the same number in order for the multiplication to even work. And then if the multiplication works, then the outside numbers are the dimensions of the new matrix. Right? So AB is going to have dimensions m by p. Well, what I could say is, so AB will be a m by p matrix. Okay, m by p. Okay, right, and so this is kind of the prereq for multiplying matrices. Right, you have to first of all determine whether matrix multiplication is defined using the columns of the first matrix and the rows of the second matrix, i.e. the inside numbers. And then once that's done, the dimensions of the product are determined by the outside numbers. Okay, let's do an example. Let's do an example here. We won't do the multiplication yet because we haven't talked about how to do it. But if A is 2 by 3 and B is 3 by 2, then can we multiply A and B? Well, yeah, so we can do the product AB, right? A times B is defined because, right, remember you got a 2 by 3 multiplied with a 3 by 2, right? So here they agree, these are equal. Okay, and AB will be a what size matrix? Well, remember that's the outside numbers. It'll be a 2 by 2 matrix. Okay, so if A is 2 by 3 and B is 3 by 2, then AB will be a 2 by 2 matrix. What about BA? Can we multiply BA in this case? In this case, it works, actually. So BA is defined because, well, B is a 3 by 2 matrix, and A is a 2 by 3 matrix, right? So the inside numbers of the dimensions match. So we can do the multiplication, and what do the dimensions be? So when we multiply them together, we'll get a matrix BA, and it will be a 3 by 3 matrix. All right, and that's based on the outside numbers. And we'll see why all of this is true in a second, but we're just kind of creating some groundwork here. All right, very good. What about if A is equal to 1, 2, 3, 4, 5, 6, like this, and B is equal to 1, 0, 0, 3, 0, 4, like that. Can we multiply these together? Can we find the product AB? Well, AB, okay, so this is going to be, A is a 2 by 3. So we've got a 2 by 3, and we're trying to multiply that against a 3 by 2. Yeah, so this is exactly the case we just saw, isn't it? So AB is defined, right? And the product will be a 2 by 2. Okay. All right. Okay, so that's kind of the prerequisite, right? We just have to make sure we can think about that, and sometimes that's a little bit that can feel a little confusing at first. Okay, now let's go ahead and define matrix multiplication. We'll just kind of formally define it, and then we'll do a bunch of examples just to make sure that we understand this, because it can be a little bit of a tricky idea at first. Okay, so here's the definition. If A is an m by n matrix, okay, and B is an n by p matrix, okay, so A is m by n and B is m by p, just like the previous examples we've been talking through. Then their matrix product, and we'll call it C and let it be equal to A times B. Okay, so their matrix product, C equals AB, is the m by p matrix whose ij entry is the dot product. Okay, it's the dot product of the ith row of A with the jth column of B. Okay, and so I know that's not on the surface that this does perfectly encapsulate matrix multiplication, but I recognize that it's not completely obvious what is happening here. But let's talk this through, and then we'll draw some pictures, we'll do some additional examples. So if A is an m by n matrix and B is an n by p matrix, exactly the dimensions that we talked about before, then I can multiply them together to get a new matrix C, which is equal to A times B. And that new matrix is going to have the dimensions m by p, right? And the new matrix is going to be built entry by entry using the dot product, where the ij entry is going to be the dot product of the ith row of A with the jth column of B. Okay, let's draw a picture. Okay, so I'm going to do a little A times B here. Okay, so bear with me. This will take a second to write this all out, but A is going to be the matrix A11, A12, A13, dot, 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 A1n. And then we'll put a couple rows in here. A21, A22, A23, dot, 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 A2n. And it says up here the dot product of the ith row of A, so I'm going to put in the ith row just for reference. AI1, AI2, AI3, dot, 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 AIN. Okay. And then, of course, this A is m by n, so I've got my n columns. I need m rows, so we'll go down to AM1, AM2, AM3, dot, 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 AMN, right? So here's an entry by entry version or depiction of what A looks like. right? So it's going to have row 1, row 2, row I, and row M. Okay, and it's going to have n columns. Now what about B? Well, B is n by P, so let's put B in here. We'll have B11, B12, B13, dot, dot, dot. Now, for B, it's the jth column that's interesting. So let's put in B1J. That's the first row jth entry, all the way over to B1P. Okay, let's put another row just for, so 21, B22, B23, dot, 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 B2J, dot, 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 B2P. Okay, and let's put another one just to make the picture nice. B31, B32, B33, B3J, dot, 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 B3P. And then we'll just go all the way down. Remember, B is going to have n rows and P columns. So we've got the P columns here. Now I need to go down to BN1, BN2, BN3, dot, 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 BNJ, dot, 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 BNP. Okay, so here's my A and my B kind of written out in component form. Okay, now these are going to produce a matrix C, which I will denote using entries that are, little c's. So we'll have C11, C12, dot, 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 C1J, dot, 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 C1P. So that's the first row, right? So it's going to have M rows and P columns. So I've got my P columns. So then the second row will be C21, C22, dot, 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 C2J, dot, 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 C2P. Okay, now let's jump down to the ith row. So CI1, CI2, dot, 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 and here's CIJ. Okay, and then let's jump down just so we have the dimensions in here. So CM1, CM2, dot, 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 CMJ, dot, 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 CMP. Okay. Okay, and then this is going to be our C. Okay, so what the previous definition says is that the IJ entry, the IJ entry of the new matrix C, so let's circle that. So that's this one right here that I've drawn. The IJ entry of the matrix C is the dot product of the ith row of A. So let's find it. So this is A, and I've drawn in the ith row. So it's this vector. You can think of this as a vector dotted against the jth column of B. Okay. And so whatever these numbers are, you're going to use the dot product to combine them. And remember, the result of the dot product is always a real number. And so that's going to become a new entry in the matrix C. So you can see why the dimensions have to have a certain constraint, right? So we said that the number of columns of A, so n of them, 1, 2, 3, dot, 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 up to n, has to be equal to the number of rows of B, 1, 2, 3, dot, 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 up to n. Okay, and that's because the dot product is only defined on vectors that have the same length, right? So this vector has length n, this vector has length n, so I can dot them together to get this new number in the matrix product. Okay. And so similarly, like if I wanted to know what the value of C11 is, if I wanted to know this one, what would I do? Well, I would take the first row of A and I would dot it against the first column of B. If I wanted to know C12, what would I do? Well, it's the first row, so again, it's the same row as before, dotted with the second column of B, right? What about CMP? What about this one? Where's that come from? Well, it's the mth row of A, so it's this one here, and it's going to be dotted against the pth column of B. That one there. That's the idea. Okay, we'll do a lot of examples here in a second, but that's the basic idea. You're always dotting a certain row of A with a certain column of B. Okay, the 1, 1 entry will be the first row and the first column. The 1, 2 entry will be the first row and the second column. Right? The ij entry is the ith row and the jth column. Okay. Another way to write this ij entry is as a sum. Cij can be written as the sum of ai1 times b1j plus ai2 times b2j plus dot 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 plus ain times bnj. Okay, and that's going to be equal to, we can more concisely write it as the sum from k equals 1 up to n of a I k times b k j. This is just a helpful way to summarize the dot product for the Cij entry is using this. Right, so the C11 entry would be equal to the sum for, as k goes from 1 up to n of a1k bk1. The C12 entry is going to be the sum from k equals 1 up to n of a2 a1k bk2. Right, so you see these are based on those subscripts, right? So the subscripts kind of follow through. Okay. All right. So this is all very nice. Maybe we have an idea that it's the ith row and the jth column for the ij entry. But let's do some examples and see how this works out in practice. Let's try a few examples here. Okay, and there's no question, this takes a little bit of practice. I mean, like everything in math, right? Nothing comes immediately. You have to kind of think it through. So we want to find C equal to AB, where A is, let's say, 5, -1, 4, -3, 6, 0, and B is equal to this larger matrix, 9, 4, -8, 2, 7, 6, -1, 0, -2, 5, 3, -4. Okay, so I've got these two matrices. So we want to multiply them together in the order specifically of A, B. So let's look at AB first. Let's double check that the dimensions make sense. So A is 2 by 3 and B is 3 by 4. Okay, so we're good. Matrix multiplication is defined. AB will be a 2 by 4 matrix. Okay, so let's go ahead and calculate this. So let's start with C11. Okay, let's talk about what C11 is going to be. So C11 is going to be the first row of A, right? So that is 5, -1, 4. We're going to dot that with the first column of B, so 9, 7, -2. Right? So remember the dot product is a simple thing. It's 5 times 9 plus -1 times 7 plus 4 times -2. Right, and when you do that, what do you get? 45 minus 7 minus 8, and I think that's 30. Okay, so the C11 entry is going to be 30. Okay, so if C is equal to a 2 by 2, it'll have C11, C12, or sorry, 2 by 4, it'll be C11, C12, C13, C14, C21, C22, Z23, and Z24. It'll look like that. And so what we've just determined is that the first entry is 30. Okay. What about the C22, for example? Okay, so C22 is going to be the dot product again. It's going to be the dot product of the second row of A and the second column of B. And so that is going to be -3, 6, 0 dotted with 4, 6, 5. 4, 6, 5. Okay. And so when you do that work, you will see that C22 is equal to 24. Okay, and so on, right? So this one is 24. And when as you go through the whole matrix, if you spend the time, you'll be able to find all the entries. Now this is a little bit larger product than on average for calculating by hand. Of course, a computer can do this in a microsecond, but humans, it takes a little longer because we have to stay oriented. Okay, so let's think about another way to kind of visualize this calculation. Let's say I want to multiply AB. Okay, so I can write the matrix out here: 5, -1, 4, -3, 6, 0. Right, and then I can say, okay, I got to rewrite this: 9, 4, -8, 2, 7, 6, -1, 0, and -2, 5, 3, -4. Okay, and so the first thing I'm going to do is I'm going to go like this: 5 times 9 is 45, plus 7 times -1, plus 4 times -2. That's the first entry. The entry right below that is going to be -3 times 9. Well, that's -27. Well, let me just write it in. If you can do it in your head, that's fine. Plus 7 times 6, plus 0 times -2. Okay. And then, so that gives me the first row, first column, and the second row, first column. Well, what about the next one? Now I'm going to go into row 2. Right, so that means basically it's going to be the same rows from A, but now I'm going to multiply them against column 2. So there'll be 5 times 4 is 20, plus -1 times 6 is -6, plus 4 times 5 is 20. Okay, and then that gives me the 1, 2 entry. Now I need the 2, 2 entry. So second row, second column. So -12 plus 36 plus 0. Okay, and now I'm half done already, right? And I could continue to fill this out, right? And I would get a -27 here, and I'd get a -6 here, and a -6 there, and an 18 here. I kind of have done this work ahead of time, right? And so one way to do it is to kind of just set up the dot product, right? To kind of go through it and just write it out like this, and then, you know, come back through a second time and kind of simplify everything. So 30, 34, -27, -6, and then 15, right? This here, if you go through this, is equal to 15, and this is equal to 24, and then 18 and -6. So that's sort of the slightly better way to think about these matrix multiplication problems. Okay, let's do another example. I'm going to write out 5 different matrices. So consider the matrices. Okay, and we're going to have D, which is -2, 1, 0, 5, and 4, -3. So it's a 3 by 2. E, which is going to be a 2 by 2, so 1, -6, 0, and 2. And F, which will be a 1 by 3, so -4, 2, and 1. G will be a 3 by 1, and it'll be 7, -1, and 5. And H is a 2 by 2 as well, and that's going to be 5, 0, 1, and -3. Now the question is, what matrix products are defined? Okay, so which of these can we multiply together? Okay, and then we'll do some examples of actually multiplying together. First, let's look at these and say which of these can actually be multiplied together and in what order. And then we'll secondarily come through and do a couple, for example. So let's think about the dimensions. So D is 3 by 2. E is 2 by 2. F is 1 by 3. G is 3 by 1. And H is 2 by 2. Okay, so kind of keeping those numbers in mind, which of these can we multiply together? Let me just rewrite them on this page here. D is 3 by 2, E is 2 by 2, F is 1 by 3, G is 3 by 1, and H is 2 by 2. Okay, so I've got the matrices actually written out there. Now, which of these can I actually multiply together? Well, let's just start with D, okay, and C. Can we multiply D and E? So D times E, that would be a 3 by 2 multiplied with a 2 by 2. Yes. What about D and F? That's a 3 by 2 trying to multiply against a 1 by 3. That's a no. What about D and G? 3 by 2, 3 by 1? No. What about D and H? 3 by 2 and a 2 by 2? Yeah, that works. Right? These match. Okay, so DE and DH work. What about E? If I have E as the first matrix, which ones can I multiply it against? Well, I just need the number of rows to be equal to 2, so E can be multiplied with H and itself, basically. So E, H, and E, E. Right, so E can be multiplied with itself. It could also be multiplied with H. What about F? F is a 1 by 3, so are there any matrices that have 3 rows? Yep. G and D do as well, right? So F and G and F and D. Those both work. Okay. What about G? G is a 3 by 1. Are there any matrices that have 1 row? Yeah. G and F, right? That one will work. Those two will work. Okay, notice F and G doesn't work. Oh, sorry, F and G does work. Yeah, we did that up here. 1 by 3 times a 3 by 1 works as well. Okay, perfect. And what about H? Well, H can be multiplied with E and itself. Right, any square matrix can also obviously be multiplied by itself. Right, so H works with itself. It also works against E. Now notice something here. Notice that if I take, let's see, F times G, so that's a 1 by 3 multiplied against the 3 by 1. Then FG is going to be 1 by 1. And so FG will be a 1 by 1 matrix. What about GF? Well, GF is 3 by 1, and G is 3 by 1, and F is 1 by 3. So just by switching the order of the matrices, I get a 3 by 3 matrix. Right, so FG is 1 by 1, and GF is 3 by 3. Okay, so that's kind of interesting. It obviously points out that the order of the multiplication is extremely important. Okay, the order of the multiplication is extremely important. Okay, let's talk about what can happen here with the order. So order matters. Okay. First thing that can happen is neither product may be defined. Right, so an example of that is DG and GD, for example. Right, if you look up here, D is 3 by 2, G is 3 by 1. If you multiply those, D times G doesn't work, and G times D doesn't work either. Okay, so that one's out. The other thing that can happen is one product could be defined, but the other may not. Right, so an example of that would be DE is defined and ED is not. Okay, remember D is 3 by 2, E is 2 by 2, so D times E works, but E times D does not. Right, D times E works, 3 by 2 times a 2 by 2 works, but E times D does not work. A 2 by 2 multiplied against the 3 by 2 does not work. Okay, so there's 4 things that can happen. The third thing is both products can be defined, but the results may have different dimensions. Both products can be defined, but the products may have different dimensions. Right, so we saw FG is 1 by 1, but GF is 3 by 3. Okay, so that's another thing that can happen. And then the last thing that can happen is that both products may be defined and the dimensions may agree, but the resulting matrices may still vary. So both products may be defined and the dimensions may agree, but the matrices may still vary. Okay, and so an example there is EH and HE. Oh, I keep writing EX. EH and HE are both 2 by 2, but they do not agree. EH is not equal to HE. Okay. Let's actually calculate these two matrices. So let's remember that E was equal to 1, -6, 0, and 2, and H was equal to 5, 0, 1, -3. Okay, so let's multiply these together in both directions and see what we get. So we'll start with EH. Right, so it's going to be 1 times 5 is 5, and then -6 times 1 is 1. So 5 minus 6 for the first entry. And then 0 plus 2. So 0 times 5 is 0. 2 times 1 is 2. So 0 plus 2. Okay, and that gets us the first column. Now the second column would be 1 times 0. Oh, that's 0. Plus negative 6 times negative 3. Okay. And then you're going to have 0 times 0 plus 2 times negative 3. Okay, so you kind of go through. So this times that, plus this times that, plus this times that. All right, so you got the whole thing. So you got negative 1, and then 18, and then 2, and then negative 6. Okay, so that's EH. What about HE? Well, it's not going to be the same thing, right? So here we have to, so it's actually helpful to rewrite the matrices, actually. Let's rewrite them here. So H is equal to 5, 0, 1, negative 3, and E is equal to 1, negative 6, 0, 2. Right, so HE, so that's 5 plus 0. And then it's 1 minus 3. 1 plus 0, sorry, 1 plus 0. And then it's 5 times negative 6, so that's negative 30 plus 0. And then it's negative 6 minus 6. Okay, and so what do you get? You get 5, negative 30, 1, and negative 12. Right, so EH is this guy, and HE is that guy, and they're not equal. Okay, perfect. Right, and so most of the time this is the case, right? Most of the time the order, even if both products are defined, the two matrices are not equal. Okay, so in the unusual case, however, in the unusual case where AB equals BA, we say that A and B commute. Right, this is the commutative property. Right, 2 times 5 is equal to 5 times 2. Now, in general, matrices don't have that property, but some do. Some actually do, and we'll see later what those look like. But in general, matrices do not. Matrix multiplication is not a commutative operation. There are obviously a subset of matrices where it does work, and in those instances when it does work, when AB is equal to BA, we say that those two matrices A and B commute. Okay, perfect. All right, now let's go ahead and jump into a kind of a theorem that describes some of the properties of matrix multiplication, right? So it's not too laundry listy, but a little bit. So suppose A, B, and C are matrices for which the following sums and products are defined. Okay, so we're not going to worry about dimensions right now. We're just going to assume for the couple of items that follow that A, B, and C have the requisite dimensions. All right, so we're just going to assume that the sums and products are defined, and obviously that's a consideration you'll have to take into account, but we're going to assume that these matrix products and sums all are defined. Okay, and if that's the case, let's also let C be a real number. We're going to need a scalar here. Okay, then the first thing is the associative law. It does work for matrix multiplication. So if I have three matrices, A, B, and C, and I start by multiplying B and C together to get a new matrix, and then I multiply again with A, then that is going to be equal to A times B multiplied with C. Right? So in this sense, it doesn't matter if I multiply B and C together first and then multiply by A, or if I multiply A and B together first and then multiply by C. Now notice the order matters. A, B, C, that has to stay the same. But the order in which I do them doesn't. So this is the associative law. Okay. The distributive law works as well. So A times the sum of B plus C. So if I have two matrices B and C and I add them together and then I multiply by A, it's the same thing. I get the same result as if I multiply A and B together first, and then I multiply A and C together, and then I do a matrix sum on them. This is the distributive law. Right? What we're used to. And then the same thing from the other direction is fine as well. So A plus B multiplied by some matrix C is going to give the same result as A times C plus B times C. So again, distributive law. All right. And then the associative law with the scalar. Right? So it's important. This is a little c. This is a little c, and that's a kind of a big C, right? So the last one is if I have the matrix product AB and I multiply the scalar C times AB, I'm going to get the same answer as I would get if I multiplied C times A first and then B. Or if I multiplied A times the matrix C times B, right? C being the scalar. Right, and so this is the associative with scalars. So it's the associative law with scalars. All right. Okay, now some of these are easier to prove than others. In particular, one can be a little bit tricky. And I'm not going to prove all these, but I will prove, let's prove two. And we'll start with two. The other 3 and 4 are kind of similar to 2. Right? They're not harder, but let's start with 2. So we want to show that A times B plus C equals AB plus AC. Now, there's really two things we need to show, right? We first need to establish that the two matrices have the same dimension, right? We need to show that this side has a certain dimension and that this side has the same dimension, okay? And then what we need, so once we establish that, then what we need to show is that the ij entry of both matrices is the same. Okay, so we'll start with the dimension argument. So first show that A times B plus C has the same dimensions as AB plus AC. Okay, so that's what we're going to start with. All right, and so we can just kind of reason through this. It's fairly easy. So we'll let A be m by n and B be n by p. Okay, so we've got m by n and m by p, and so the multiplication is going to work if those are the dimensions. And so we'll start with A times B plus C. Okay, so B is m by p, and let me put those in parentheses. C is m by p. Sorry, I forgot to say that. We want to let C be m by p as well up here. Okay, so A is m by n, B and C are both m by p. Okay, so B is m by p and C is n by p, and so when I add them together, what do I get? Well, that's going to imply that B plus C is n by p. Okay, A is m by n, and B plus C is n by p, as we just showed. That's going to imply that A times B plus C is m by p. Okay, perfect. All right, what about the dimension of, so that's this guy. What about this guy, A times B plus, oh, sorry. We did this one first. Yeah, sorry. A times B plus C is m by p. What about A times B plus A times C? Okay, let's look at that one next. Well, A is m by n, and B is m by p. So A is m by n, B is n by p. Right, that those two facts together implies that A times B is m by p. Right, this is all just definition, right? The definition of multiplication. Okay. Again, similarly, A is m by n, and C is n by p. And so that implies that AC is m by p. Okay, and now what happens if I add two matrices together and their dimension is m by p? Well, obviously the sum is m by p as well. AB and AC are m by p, and that's going to imply that AB plus AC is m by p. Okay, and so that's exactly what we need to show for this first part. Right, so the two matrices have the same dimensions, which means they have the same number of entries, right? And so now all we need to show is that an arbitrary entry from each of these matrices is going to be calculated the same way. Okay, so let's see. Let's see if that works. Okay, so A times B plus C and AB plus AC have the same dimensions. What about the IJ entries? What about the IJ entry? Okay, so what we need to do is basically show that they're the same, right? So let's start with AB plus AC. Okay, so we'll start with that one. So let's write out what the IJ entry of AB looks like. So A times B, the IJ entry. Well, this is the matrix product, right? So A times B. So I'm basically going to take the ith row of A, and I'm going to dot it with the jth column of B, right? And we talked about a nice way to represent that is like this: sum over K of A, I, K times B, K, J. That's ABIJ, right? It's the dot product of the ith row of A and the B and the jth column of B. Okay, what about AC? What's the IJ entry of AC? It's the same thing, right? I mean, it's the ith row of A and the jth column of C. So it's equal to the sum over K of A, I, K times C, K, J. And so then obviously if I add the two matrices, we know that that is component wise, so that's just adding the IJ entry from AB to the IJ entry from AC. And so if I take AB plus AC, the IJ entry there is just going to be the sum of these two. Right, just like this. Okay, and a better way to write that is to combine the sums. So the sum over K of A, I, K, B, K, J plus A, I, K, C, K, J. Okay, and so this is the IJ entry of the first matrix, AB plus AC. Now what about the second matrix? So next we'll look at A times B plus C. What is the dimension, or sorry, what is the ij entry for this matrix? Okay, so we need to know A times B plus C, right? That whole matrix, the ij entry. Well, basically this comes down to a multiplication product again, right? You've got the A matrix multiplied with this matrix B plus C. Okay, and so the way we can write this, it's going to be the ith row of A and the jth column of B plus C. Right, so we can write it like this. Sum over K of A, I, K times, now here we are dealing with a matrix B plus C. So B plus C is going to be the KJ entry there. Right, so we're going to range over all of the rows of the jth column. Okay, and then we can break this down further by writing the sum over K of AIK times BKJ plus CKJ, right? So this will, again, this will be just a sum, right? So it's BKJ plus CKJ. Okay. Hopefully that's clear. Like sometimes this notation can be a little tricky, but there's kind of really no better way to kind of write this. And then these are just real numbers, right? So the distributive property works on real numbers. So 5 times 7 plus 6 is the same as 5 times 7 plus 5 times 6, right? And so we know that, and so we can expand this, and we see that we get AIK times BKJ plus AIK times CKJ. Okay, and you can see for yourself that those are the same, right? They are the same. That's the same ij entry. So the ij entries are the same, and the dimensions are the same. And so that implies that A times B plus C equals AB plus AC, right? So that's the end of the proof. So that's the proof of property 2. Now 3 follows almost exactly the same. 4 is similar, but not exact. And then 1 is a little more tricky, a little trickier, a little longer, but I think you could handle it. Okay, perfect. All right, so I think I'll pause the video here and we'll have a part B for this section. It's a little bit longer section. So I'll go ahead and pause the video here and we will come back and talk more about matrix multiplication in a minute.